Now that we've talked about the subatomic particles and some of the things we can get from the periodic table, let's talk about the other piece of information that's in that periodic table box, okay? We've talked about the number at the top there, the 6 in the instance here in our example that I have drawn. That's the atomic number, which is equal to the number of protons. The number at the bottom, this 12.011, is the atomic mass. Now here we have a definition for atomic mass. It is the weighted average of all possible isotopes of an element. So by weighted average, what we mean is it takes into account the percent abundance. Okay, so the isotopes are made up of different numbers of protons and neutrons, and they make up a different percentage of the element. So not the isotopes aren't weighted equally. Okay, we had carbon 12 and carbon 14 in a previous video. Carbon 12 makes up like 99.8% or something of the carbon. The other 0.2% is carbon 14. So the mass is going to be closer to 12, which is why you see our atomic mass is 12.011. Okay? So to get the overall atomic mass, what would be reported on the periodic table in the box? We take the sum. When you see this little Greek symbol, it's the Greek sigma. It means the sum, so add them up, of the fraction of the isotope times the mass of the isotope. So if the abundance is given in percentages, you need to change them to fractions or decimals. So remember from math, to change a percent to a decimal, we move the decimal 2 places to the left. Okay, so I'm going to go ahead and do that on all of these percentages that are given first. And then I think it's easiest to set it up in a little table, basically, where you take the mass for an isotope and you multiply it by its fractional abundance. And then you take the mass of the second isotope and multiply it by its fractional abundance. And then finally the third isotope and multiply it by its fractional abundance. And so you're going to get 3 separate answers here: 18.95, 2.499, and 2.860. And then since it's the sum of them, you add them together. And so we get that the atomic mass of magnesium is 24.31 AMU to significant figures with the numbers we have. If you go and look at a periodic table, magnesium's mass is listed as 24.31. Okay? That's where that number comes from, the 3 isotopes of magnesium. We can also use it to kind of backtrack to the mass of one of the isotopes. If we know information about the other isotopes of the element, and we know what the mass is supposed to be on the periodic table, then we can figure out the mass of a missing isotope. So this could be used in helping to discover new isotopes or something like that. Okay? So we have gallium here. It occurs as 2 naturally occurring isotopes. There's gallium-69, and it tells us its mass is 68.9256 AMU. And its abundance is 60.11% or 0.6011. So we can go ahead and write that one out just like we did on the previous example. Use the atomic mass of gallium from the periodic table to determine the mass of gallium-71. So we're trying to find the mass of gallium-71. And we go to the periodic table and look up the mass of just gallium, of the overall element. It is 69.723. That's its mass on the periodic table. So we still kind of have 2 variables here because we don't know the mass. That's what we're trying to calculate. But we also don't have the abundance for gallium-71. We can figure that out, though. If there are 2 naturally occurring isotopes, then their abundances have to add up to 100%. So if the first one is 60.11%, then the second one is going to be 100 minus 60.11, or 39.89%. Move our decimal back to get our fractional abundance. And now we have one variable, one equation, we can solve it. So when I multiply the 68.9256 by 0.6011, I get 41.43. I'm going to add that to x times 0.3989 and set that sum equal to 69.723. And now it's just a little bit of algebra. Okay, we'll subtract the 41.43 over, and get 28.293. And then we'll divide by 0.3989. And my unit is going to be atomic mass units because we're trying to find a mass. It's a good idea to stop and make sure it makes sense. If this is called gallium 71, the mass should be close to 71. So 70.93 would round to 71. So you might wonder, where do we get these numbers? We can't always isolate an isotope, and we sure can't isolate one atom of an isotope and stick it on a scale and weigh it. Okay? We have a technique called mass spectrometry that allows us to separate particles out by mass. It can be used for compounds to help you identify compounds, but it's also been used to figure out the atomic mass of elements by looking at the different isotopes of the element. So we have a real simple example of a graph right here. The intensity is related to the abundance. So you can think about it in terms of the abundance. And then the x-axis is the mass. So we have chlorine here. It's got two isotopes, chlorine 35 and 37. So I'm going to make myself a table. So we have 35 and 37 for the masses. For the abundances, this chart's not great, so we're going to have to do some estimating. But it looks like chlorine 35 is right at 100. And I estimated 37 to be right at about 35. You might say 40. That's okay. It's an estimation. So to find the overall atomic mass of chlorine, we've got to find the relative abundance. Okay? So to find the relative abundance, you take the abundance of each element divided by the total abundance for all of them. So we're going to add this together and get 135. And then we'll take the mass of the first isotope times its abundance over the total, plus the mass of the second isotope times its abundance over the total. And if there had been 15 isotopes, you could just do that for all of them. And when you add that together, we get 35.5, which is a pretty good estimation for chlorine. If you go look it up on the periodic table, it's 34.453. Excuse me, 35.453. And so that rounds to 35.5. So we'll do some practice with mass spectrometry in class. Unfortunately, we can't run our own because it's a very expensive instrument, but we can learn how to analyze those graphs.